Listen-only mode.
Hello and welcome everyone to the first session in our GenScript webinar series. My name is Keshav Vasantavada and I'm a marketing specialist for protein services here at GenScript. Prior to joining GenScript, I worked for 7 years in a big pharmaceutical company in their core facility, performing cloning, expression and some purification of a variety of disease targets. While I have hands-on experience with different expression systems, my work has predominantly been in E. coli. Among other things, I have experience in the development of novel fusion partner technology for recombinant soluble protein production and the implementation of automation and liquid handling systems in performing small-scale expression studies in a high-throughput fashion. And in line with my background, the topic of my talk today is optimizing conditions for recombinant soluble protein production in E. coli. So as scientists in the life sciences area, we all realize at some level the importance of recombinant soluble proteins in discovery research. E. coli is a popular choice for the production of these proteins, and in this webinar we are going to review what we found are the most important optimization parameters that influence soluble protein expression in E. coli. In doing so, we leverage the collective experience of a production team that has generated over 3,000 batches of high-quality, pure recombinant protein so far. We hope that this session will help you build a better E. coli expression strategy while avoiding common pitfalls in your experimental design. If you have questions during the presentation, you can submit them by typing them in the questions field that should be showing up on your screen right now. I'll do my best to answer some questions at the end of the session, and for those that I cannot answer today, I'll make sure we post it on our website as soon as possible. If you're unable to sit through this presentation, you can check back our website www.genscript.com to view this archived webinar and links or downloads of any associated material presented today. So this presentation is broadly divided into 5 topics, and the conclusion, we'll do a brief introduction about GenScript, then look at the historical perspective of recombinant DNA and protein expression technologies. We'll discuss the topic today and look at some of the key aspects to consider before embarking on a protein expression project. We'll focus on concerns and aspects of E. coli expression and look at the solutions that GenScript has come up with to address some of the challenges in E. coli expression. Then I'll list out what we think are some of the most important factors that contribute to recombinant protein solubility, and then take a look at some case studies before concluding the presentation. I'll answer user-submitted questions towards the end. So about GenScript, headquartered in Piscataway, New Jersey, GenScript is the world's leading biology research service company with gene synthesis, peptide, protein, antibody, cell line, and discovery biology service capabilities. We are internationally recognized as a leading contract research organization specializing in biological research and early phase drug discovery services. We provide services and products to scientists in 86 countries around the world. We have built the best-in-class capacity and capability for biological research services encompassing gene synthesis and molecular biology, peptide synthesis, custom antibodies, protein expression, antibody and protein engineering, and in vitro and in vivo pharmacology. Now all this with the goal to make research easy. As of 2013, more than 9,000 peer-reviewed journal articles cited GenScript's services and products, making GenScript the most frequently cited biology CRO in the world. So moving on, looking at a historical perspective, you can see that the idea that protein could be the product of a gene was formulated as early as in the 1940s. The molecular biology landscape changed quite dramatically since the elucidation of the DNA structure and subsequent discovery of restriction enzymes. The birth of recombinant DNA technology in the 1970s spurred the growth of the biotech industry, with Genentech at its forefront, and techniques like DNA sequencing, PCR, and affinity purification of tagged proteins continue to shape new discoveries while maturing the science further. Now I wonder what the next big thing in this evolution is. Synthetic genes had transformed the way molecular biology was performed, and GenScript helped shape that revolution with its leadership in gene synthesis services. I wonder what's next from a protein biochemistry standpoint. GenScript can already synthesize proteins up to 200 amino acids in length. So are we looking at full-length synthetic proteins, just like full-length synthetic genes? Maybe. In one of my lab fantasies, I always thought it would be cool, if we discovered an enzyme that could amplify proteins. Using a small amount of protein as a template, it should do exactly what the Taq polymerase did for DNA. Now that would be simply awesome, because then we wouldn't have to express proteins anymore or go through the motions of optimizing expression conditions. Well, maybe that's just science fiction for now, but until we get there, I have some tips for you that might just make the process easier. So we know that recombinant protein production is an essential step for functional characterization and structure determination of proteins, and while a variety of hosts are available for this purpose, the gram-negative bacteria E. coli is often considered the workhorse of researchers around the world, and hence my talk today will focus on recombinant protein expression in E. coli. Most of you know that the successful implementation of a bacterial protein production project depends on a variety of factors. Today I will provide some observations and a few recommendations for optimizing recombinant protein expression in E. coli. In doing so, I'll leverage the collective experience and learnings of our production team that has shipped well over 3,000 batches of recombinant proteins so far. A typical starting point for most expression projects begins with asking the most basic question. Why do I need this protein? Is it for an activity assay? Is it for biochar? Maybe structure biology work or high throughput study? And this is important because the end dictates the means. That is, in many ways, the application will dictate to some degree the host choice, purity requirements, construct design, tags, etc. However, the truth of the matter is that for most scientists, recombinant protein is used in multiple applications. Regardless, the answer to this question needs to be thought through before embarking on your mission. The second, but equally important consideration is the host. Traditionally, recombinant proteins have been made in hosts like bacteria, insect cells, yeast cells, or in cells of a mammalian origin. There are also kits available that would allow you to make protein in vitro using a cell-free translation system. Now, given this kind of choice, how do you select which expression system to use? Now, while there are various factors that go into the decision-making process, nature of the target protein and its solubility, its functionality, protein yield requirements, user experience, intended applications, and the speed of generation are often some of the most important factors that govern the decision. And in this regard, E. coli has often been considered the #1 choice of researchers around the world. And this statement is attested by the number of entries in the protein data bank by expression system as a percentage of the total number of chains with an identifiable expression system. Data here shows the dominance of E. coli expression system. So we know that E. coli is the top choice, but what makes it favorable and what are some of the disadvantages? A combination of simple genetics, ease of culturing and scalability, fast expression in high yields, makes it an attractive choice, while the lack of an efficient post-translational machinery, codon usage bias, and difficulty in producing high molecular weight proteins makes it disadvantageous. However, one of the biggest evils in E. coli expression, which is nearly as bad as low expression or no expression, is insoluble expression. As all of you will be familiar with, this is a phenomenon when overexpression results in the formation of insoluble aggregates called inclusion bodies. So what's the problem and what are the solutions? Let's recap the possibilities in an E. coli expression project. So here are two of the most likely scenarios you encounter when expressing your target protein in E. coli. #1, which is the most favorable outcome, would be that you're able to overexpress your protein in a soluble fashion in the bacterial cytoplasm. Everyone is happy. Or you could try overexpression, but due to anomalies in protein folding, the protein ends up as insoluble aggregates called inclusion bodies. And when that happens, you could try a very cumbersome process called in vitro protein refolding and solubilization and still get the necessary outcome. Or you could try optimization at the process or molecular levels. At the process level, you could just adopt methods that do not require target engineering. For example, you could play around with the expression conditions, like trying out different strains, adjusting the growth and induction conditions. You could change media, buffers, you could try out chaperone co-expression, and in some cases even improve the cell lysis conditions. As an alternative, you could manipulate your target protein by eliminating the undesirable elements within its sequence by creating truncations or mutating certain amino acids to make the protein more soluble. Here you could adopt a rational site-directed mutagenesis approach based on structure information, or take a directed evolution approach and screen for the solubility of random point mutants, deletions, and fragments. A better, easier approach would be to adopt a fusion partner strategy and use a solubilizing partner upstream of your target protein to make it more soluble. So why is target protein insolubility such a big deal? Just to give you a perspective of how bad the insolubility problem is, we have the statistics from the Northeast Structure Genomics Consortium's website that indicates that out of the approximately 24,000 constructs that were expression tested, almost 43% were found to be insoluble. So as you can see, target protein insolubility is indeed a significant problem. And speaking of insolubility brings me to state the premise of most protein production projects, which is the generation of high yields of soluble protein in a cost-effective and expeditious manner is the single most important determinant of a successful protein expression campaign. That is, all these variables in your expression need to go through a carefully crafted funnel of optimization in order to yield some soluble protein. Now, I know there will be skeptics out there who will tend to disagree, and of course with reason. Solubility need not be the be-all and end-all of a protein expression campaign, but for most purposes that is the case. So having established that, let's now take a look at what a typical protein expression workflow looks like. And while I show this as a sequential chain of events, you know that some of these steps work in parallel. So after a project has been initiated, the first logical step is literature review, wherein you scour the web to see if there is a literature precedent for your target protein. That is, maybe it has been produced already by another group. If so, can you get the protocol and reproduce it? So again, while this is a necessary step, all bets are off because you know that reproducibility in life science is not guaranteed. So what has worked for one group need not work for you, even with the same target. So with or without literature precedent, we move on to the next step, which is target analysis in engineering. It would be good to know if the target was expressed full length, which would be the best case scenario. An initial analysis of the primary sequence will tell you if the target will be a challenge to produce. There are recombinant protein solubility prediction programs, which will tell you the probability that your overexpressed target will be soluble in E. coli. While the output is just a mathematical number and not a guarantee of solubility, it's a decent and fairly easy exercise to perform, and it will give you some idea of your protein's expected behavior. Other considerations are, will you make tagged protein or will it be tagless? Will you place tag at the N terminus or at the C terminus? What will be the cleavage tag? And we already reviewed the host consideration parameters earlier. So once you design the target, you begin the cloning scheme next, right? Typically, many researchers these days, they tend to adopt parallel strategies to facilitate high throughput cloning and expression. So for example, strategies like ligation-independent cloning or recombination-based cloning will allow you to generate multiple expression constructs at once for parallel expression testing, which I think is a good approach. While ligation-independent cloning is friendlier, in the sense it adds minimum vector residues and is perceived as more friendly to crystallography, recombination-based cloning is also a very efficient method. With the advent and affordability of synthetic genes, many scientists choose to have their genes designed, synthesized, and subcloned into an expression vector. So once the construct is ready, the next step is small-scale expression evaluation and optimization, with the last step being scale-up and purification. And this teardrop symbol here along this workflow symbolizes all the steps that GenScript can perform for you to support and accelerate your research. Excuse me. So this is similar to an earlier slide where we look at a bacterial expression project more closely. Once you adapt expression and see that the protein is insoluble at small scale, you could either archive the construct or scale it up and purify it. On the other hand, if the protein does not express at all, we need to review the construct carefully to make sure there is nothing wrong with it. For example, is the DNA sequence all right? Is there a frameshift mutation that results in no expression? Is the vector okay? Is the protein toxic? In case of insoluble protein, we have fold art, which is GenScript's proprietary refolding technology that combines high hydrostatic pressure techniques, small molecule additives, and column refolding methods to yield pure protein with over 95% success rate. Excuse me. We can also use Potential to perform evaluation and optimization for you. And during expression optimization, we also recommend running a small-scale test purification in order to get the most accurate report of your protein's behavior. So what exactly is Potential? It's a new protein expression evaluation and optimization service offered by GenScript. You can evaluate whether your target protein expresses in your chosen system, and you can identify the best expression system for your target protein and identify the construct and conditions that give you the most robust soluble expression of your target protein. The goal is to evaluate thoroughly before scaling up in order to save time and resources. At GenScript, we have comprehensive one-stop service that includes gene synthesis, subcloning, protein expression evaluation and optimization, all the way to large-scale protein production and beyond. So the Potential portfolio. There are essentially three different Potential packages. We have the standard package that starts at $280 US, which is available for bacterial, mammalian, and insect cell expression systems. And then we have the silver package that starts at $1,440. That is available for bacterial expression system only. It allows you to identify the best expression condition with your chosen vector and bacterial strain. The Potential Gold package is an industry-first high-throughput expression and solubility optimization matrix that tests 48 different conditions to establish the ideal condition for your target protein. An optional but recommended add-on 1 liter purification step is also available with this service. And this table here lists the prices of our Potential standard package. You can choose one or more host options, and the timeline for these services is between 1 to 4 weeks, and deliverables includes STS and Western blot data along with an expression data report. You can also get a quote for these services or order them directly from our website, and if you are our existing gene synthesis customer, this process is even more streamlined for you. Now this slide here lists some of the tag, media, and vector options. If a modification is not found on this list, the gold or silver package gives you the flexibility to make special and custom requests. We have a variety of options to choose from in the Potential Gold package. As you can see, we have lots of promoters, bacterial strain choices, and culture and temperature conditions. We can also accommodate most special customer requests. Excuse me. Now, this slide here depicts some of the parameters that impact protein solubility, and playing around with these factors could help you achieve your desired goal. And I'm just gonna let you know right now that I'll spend the next two to 3 minutes on this slide talking about the various factors that are important for recombinant protein solubility. So basically, the factors in this circle are what we think are the most important ones that one should focus upon, and the factors in the rectangles in the corners are auxiliary factors that are important but are not as important as the core factors. So in no order of preference, the most important factors that impact recombinant protein solubility are codon optimization, E. coli strain, induction temperature, and a suitable fusion partner. The auxiliary factors include inducer concentration, growth media, promoters, and the often overlooked but important aspect of induction duration. Now we'll look at the core factors in more detail in the next few slides, but let's quickly take a look at the auxiliary factors first. Inducer. And many people focus too much on IPTG concentration, but the truth of the matter is that for most proteins, we found very little difference of IPTG concentration between a 0.1 to 1 millimolar range. Now, excessive IPTG, of course, can be harmful to bacterial growth, but this is one variable that can be avoided in most cases. Now, I'm not saying that this is not important. Inducer concentration is important, but gets really critical in the micromolar range when cells have more metabolic control over toxic protein production. To be conservative and reduce the number of test conditions in my experiment, I would typically stick with 0.1 millimolar IPTG in most cases. Now, changing the inducer altogether can help though. For example, arabinose induction can be a preferred method that allows you tighter control over toxic gene expression. Changing the growth medium could help. Sometimes addition of a buffer to control pH variability in the medium can help. Addition of 1% glucose to repress the lac promoter can be helpful. Induction duration can be critical, especially for highly insoluble proteins, because in some cases, cells tend to make soluble protein in the beginning that is detectable on a Kumasi stain gel, in fact, as early as 30 minutes post-induction. Doing a time point study will tell you if there is soluble protein in the beginning that becomes insoluble over time. Of course, the amount of soluble protein made early on may be very little, so once you scale up culture volumes, you may just be able to recover enough protein for your experimental needs. I'll show you a case study later on that illustrates this point. Chaperones typically help in protein folding by transiently interacting with the recombinant protein. GrowES, GrowEL is a well-characterized pair you could try out. Foldase is like PDI or protein disulfide isomerase, DSPA and DSPC. They accelerate the rate-limiting steps in a folding pathway, and both DSPA and DSPC also function very well as fusion partners. You could also improve protein's solubility by lowering the rate of protein synthesis by using a weaker promoter like the TRAC instead of T7, or using a low copy number plasmid. So now about the key factors according to us. Codon optimization. The value of this approach has been somewhat debated, both with arguments for and against it, but with over 190 publications citing our codon optimization services and our own in-house experimental data, we strongly believe in the value of this technology. Since not all codons are used equally, the major codons are those that occur in highly expressed proteins, while the rare codons are in genes expressed at lower levels. And when the codon usage of your target protein differs vastly from the average codon usage of the host organism, this could result in decreased expression. When you have your gene codon optimized at GenScript, our proprietary optimum gene software produces over 10,000 candidate sequences during just one round of analysis. A complex sorting matrix then selects the best sequence for each specific customized request. The algorithm then optimizes a variety of parameters that are critical to transcription, translation, and protein folding, and eliminates any codon bias. We have optimized over 50,000 sequences in all major expression systems using our platform, and we found that the expression level of target proteins can be significantly improved by the use of this technology. And here are two case studies that illustrate the importance of codon optimization for E. coli expression. You can see on the top gel, in case of protein alpha, the difference in expression levels from codon optimization of a eukaryotic protein using a proprietary platform versus a competitor's is threefold. The effect is heightened in case of protein beta on the lower panel, nearly 13-fold improvement. While data is not shown here, the comparison between no codon optimization and codon optimization using our platform was also striking in both these cases. E. coli strains. Now this here is a list of some commonly used E. coli expression strains. Depending upon your initial target analysis, you can decide which one to begin with. For most purposes, the standard BL21DE3 works just fine. However, its basal level of expression is really high, so it may not be suitable for difficult targets. Now, some of these have redundant functions. For example, the origami strains, they all feature enhanced disulfide bond formation in the E. coli cytoplasm. But in addition, they may also have additional features like extra copies of rare tRNA genes or controlled IPTG entry into cells, etc. As such, they can all show quite different expression profiles even with the same target. They can be really good because then you don't have to attempt periplasmic expression of your target protein, especially if it is disulfide rich or toxic in the cytoplasm. In that case, you can go straight to the origami strain. The overexpressed C41 and C43 strains have an uncharacterized mutation that allow higher production of difficult proteins. The LEMO cells allow you to tune expression by regulating lysozyme concentration, and you could do this by adding rhamnose. There are a few other strains not listed on this in this table that do very well with toxic proteins. For example, BL21AI, which is the arabinose inducible strain, is designed to give you high protein yields with tight regulation using a T7 promoter system. We have used these and a few others with impressive results in the past. The solubility expression profile from using these strains can vary greatly, and so for a really tricky protein, you could try different expression strains while keeping all other conditions the same to see if one of these gives you the desired results before you try on other things. Now these are Kumasi stain gels that showcase the differences in soluble protein expression among the different E. coli strains used. Excuse me. The 24 lanes on the upper panel belong to a 30 kilodalton target protein A, tested in the 20 expression strains that were shown on the earlier slide. The lower panel belongs to a target protein B that was tested in the same collection. Now we are not looking to see which strain performs better, but the idea is to take note of the vast differences in soluble protein expression in the various strains. Obviously, since each protein is different, every expression profile, like a fingerprint, will be unique. Temperature. So one way to reduce the rate of protein synthesis in order to obtain soluble protein is by reducing the temperature during induction. Typically, we prefer around 15 to 18 degrees Celsius from a few hours to overnight, irrespective of what inducer you use. And in this image here, you can see how total recombinant protein is being made at 3 different temperatures, 15 degrees, room temperature, and 37, as detected by Western blot. But the protein is entirely insoluble at 37 degrees Celsius. And this here is a table of some of the popular affinity and or solubility tags. As you'll know, one way to improve the solubility of your target protein is by fusing it downstream of a soluble fusion partner. And this, in my opinion, is the best way to produce soluble protein. Of course, each tag has its pros and cons, so we need to evaluate the experimental requirements carefully in selecting the tag. Now you'll see that I put a caution beside the his tag because while it's quite universally used as an affinity tag, the his tag is not as innocuous as some would think. The his tag can affect expression levels, protein solubility, activity, stability, and even structure and function of your target protein. Now the flag tag functions very well, and it also introduces an enterokinase cleavage site. However, the resin can be a bit expensive. GST is a good solubility tag, but its dimerizing property can be an issue. NUS-A works quite well as a solubilizing partner, even with larger molecular weight proteins. What else? MBP. MBP is a highly oversubscribed fusion partner, and with reason. It works really well also, and the fusion protein is generally quite stable. Now there are other really good fusion tags that are not on this list that we have developed in-house. And while there is tremendous promise in fusion partner technology for recombinant soluble protein production, this method has its own evils. For example, while a highly soluble tag will solubilize its passenger protein, there is no guarantee that your target protein will remain in solution once the tag is cleaved off, right? Sometimes you cannot cleave your fusion partner because a proteolytic enzyme can't even reach the cleavage site because of interference from the fusion partner. Now that can happen. On other occasions, your fusion partner will start sticking to your target protein post-cleavage, right? That's a third possibility. And of course, there are other ways to address these problems during construct design and purification, but one thing to consider would be to leave the tag on, and this again depends on the application of your target protein. That is, if you can still derive biologically relevant data from using tagged soluble protein, you should consider that approach instead of going through the motions of trying to cleave off the tag and then struggling to keep your target protein in solution. Maybe in a separate session we can discuss the applications of fusion partner technology in producing recombinant soluble proteins and how to address these tag cleavage issues. But for now, let's move on. So this slide here illustrates the value of a fusion partner in producing soluble protein. These are Komatsu stain gels. On the left side image, you see target protein C, which has a molecular weight of 30 kilodaltons. It's barely seen in the soluble fraction without a fusion partner, as seen in lane 1, whereas using a 15 kilodalton fusion partner makes it robustly soluble, as you can see on lane 2. And on the right side image, we see a 15 kilodalton highly insoluble target protein is made soluble by tethering it downstream of a 45 kilodalton soluble fusion partner, as you can see in lanes 3 and 4. And by the way, both these fusion partners are novel proteins that are not on the list we saw on the earlier table. Induction duration. You'll recall I had mentioned the importance of a time point study during expression testing. Now this is a case study that illustrates the significance of duration of induction. In some cases, even with the difficult proteins, E. coli cells tend to make some soluble protein in the early stages of induction, and at some point during the growth cycle, most of the protein starts to become insoluble. Now this time point would be target specific, so it may be useful to perform a small scale study to determine what the best time to harvest your cells is. So in case of protein E on the top, you can see that the target protein starts accumulating as detected on a Komatsu stain gel as early as 30 minutes. In case of protein F on the lower left hand side, there isn't much of a difference between cells tested after a 3-hour induction versus the same cells that were continued to induce overnight. And in fact, in case of protein G, seen on the lower right hand side, there was soluble protein early on at 3-hour induction, but then most protein went into the insoluble fraction after overnight induction, even at low temperature. While these may all be different proteins, the observations I'm trying to point out to is that, number one, in some cases, it becomes important to determine the best induction duration for your target protein. Number two, longer induction times are not always good, and in fact, on the contrary, longer induction can result in insolubility issues with your target protein. Excuse me. So here are some broad recommendations regarding cloning, expression, and purification. To increase throughput, it might be useful to adopt a ligation-independent cloning or recombination-based cloning strategy. If possible, use expression vectors with N-terminal solubility partners for easy cloning of all targets. If you don't see target expression with an N-terminal construct, try C-terminal one instead. That helps sometimes. Note that if you're checking for enzyme activity, one version might show higher activity than the other. Also, a C-terminally tagged construct will allow you to purify full-length proteins, and you could also try a double tagging approach by using a solubility partner at the N-terminus and an affinity tag at the C-terminus to solubilize and purify full-length protein at the same time. So, to summarize, there is no one simple global solution to address the insolubility issues in E. coli expression. However, a well-engineered construct and a carefully crafted expression strategy can give you the desired results. Codon optimization, E. coli strain choice, induction temperature, induction duration, and most importantly, fusion partners make a difference. Small-scale expression study must be designed so it becomes predictive and so you can perform early triage of soluble constructs. Small-scale purification should be performed to assess protein's behavior and avoid any hiccups during scale-up. Parallel approaches increase the chances of success. An approach that we would suggest is combinatorial tagging at the N-terminus, so a 6-cis and a solubilizing tag at the N-terminus, followed by a protease cleavage site for tag removal after the first round of purification. And this schematic here illustrates a broad strategy. And finally, while solubility is the most important element of a protein production campaign, it is not always about solubility. Expression levels, activity, purity, homogeneity, stability are all important factors that must be taken into consideration also. And this slide here showcases our experience and capacity in producing and delivering high quality soluble recombinant proteins to customers around the world. Now this number has actually gone up even more from 3,000. Our production team has experience purifying a variety of difficult proteins, including transmembrane proteins, cytokines, kinases, viral envelope proteins, etc. You name it and we have made it. And with that we conclude the presentation and we can move on to the Q&A. I hope you found this session useful. I can see that questions have been pouring in. But before we go there, I just want to let you know that the next seminar in this series will be on the topic avoiding peptide assay failure, hidden problems and solutions. That's next Thursday, May 15th at 2 p.m. Eastern Standard Time. And this here is a list of our entire webinar series coming up. Also, as I mentioned at the beginning of this presentation, this webinar will be archived on our website and links to resources and Q&A will be posted soon. So please visit our webinar page to take advantage of these resources. If you have any questions or feedback for me, you can reach out to me directly via email. My email ID is keshav.vasantavad@genscript.com and it's listed on the top here in the slide. Also, it would be great if you could please take a moment to complete a quick poll right after this webinar to tell us how you like this presentation. Your candid feedback will help us improve our services. So let's see if you can just give me a minute here. I'm going to now scroll through these questions and do my best to answer as many as I can. If for a lack of time or my inability I cannot answer your question, I'll make sure that we post the Q&A on our webinar page. So if you just give me a minute. Okay, I see one of the questions we have is, I express human protein in E. coli without codon optimization. No expression at all. Will codon optimization help? Okay, so while codon optimizing a gene is not guarantee that you will see soluble expression, the odds will certainly improve if you use codon optimized human gene to make recombinant protein in E. coli, which is what I guess you're saying you're doing. In your case, however, since you see no expression, I would also recommend doing a thorough QC to make sure that your construct is okay. Again, your method of QC, depends upon the origin of your insert. So, for example, if you had your insert synthesized, then it's likely that they gave you the raw sequence files, so you can just make sure that everything is fine with your insert. You could also just quickly perform restriction analysis to get the big picture about your construct. But if you haven't already sequenced your DNA, I would recommend that you do perform sequencing and confirm that your insert is fine. I hope I was able to answer that question to some satisfaction. So is it possible to reduce insoluble recombinant protein with reduction temperature? If possible, how is a good temperature for this? So from what I understand, this question, is it possible to reduce insoluble recombinant? Yes, the thing is, once you lower the temperature, the induction temperature, yes, you do lower the overall protein synthesis. You slow down the protein synthesis machinery, and that really is the idea. So the thing is, if you remember the case studies, they tell you that, they show you that proteins are made at a lower level if you induce them at a lower temperature, right? But the thing is, once you go lower temperature, you give the protein sufficient time to fold properly, because you're not really cranking up too much, you're not putting too much pressure on the metabolic machinery. So that in some ways, yes, you do get lower protein, but the protein is also more soluble. What is your opinion regarding CF expression? I'm assuming CF means cell-free, in which case I think there are a few advantages to cell-free systems over cell-based systems. For example, you can express toxic proteins more easily. Isotopic labeling of proteins is quite easy, and you could express multiple proteins using one reaction mixture. However, I find that reproducibility can be an issue, and scalability can be somewhat cost prohibitive. I feel that cell-free systems should serve to supplement the existing cell-based methods. That's my personal feeling, that they should supplement the existing cell-based methods, but I don't think they can entirely substitute cell-based protein expression systems, at least not yet. What about the choice of protease tag? What about the choice of protease tag? So my personal preference is, for a long time, has been TEV, the tobacco H virus protease. I find it's quite specific. Again, I'm not endorsing one tag or another. I found thrombin a little non-specific, and so my personal preference has mostly been the TEV. Okay, thank you. I enjoyed your presentation. It was very practical and will be useful as reference for my daily work. Can you send me the slides? Well, first of all, thanks for your positive and encouraging feedback. I'm glad that you found this to be helpful material. The presentation will be available on our GenScript webinar series website, available from our homepage at www.genscript.com. You can check back later. Next question. I'm attempting bacterial expression of a highly insoluble protein without success so far. It is part of a larger complex. A friend said that I should try co-expression of both units. Is there any merit in that suggestion? Okay, let me read this again. Attempting bacterial expression of a highly insoluble protein without success so far. It is part of a larger complex. Excuse me. A friend said that I should try co-expression of both units. Is there any merit in that suggestion? Yes, there is merit in that suggestion. Your friend has a valid point. I think in many instances, proteins that are insoluble can be expressed in a soluble form by co-expression with one or more proteins that form a complex naturally, right? So typically when you express separately, the protein is not soluble because it's I believe its hydrophobic patches are exposed to the solvent, so that forces it to become insoluble. So once you express its natural binding partner, you could try a co-expression strategy. These insoluble or these hydrophobic patches can be protected, resulting in more soluble protein. But you might have to purify the whole complex, but this is certainly doable. But remember that to do this, you can try expressing using different vectors, or you could also just use one vector. Oh, and by the way, make sure that if you're using different expression vectors, both vectors should have different antibiotic resistance markers and different origins of replication to ensure plasmid stability. And if you are co-expressing from the same vector, recall that the order of genes also can make a difference. So my general recommendation would be that you have the more soluble protein upstream of the less soluble one. Okay. So how to avoid protein degradation during the protein expression process? So the best way to avoid protein degradation, in my opinion, would be to tether your target protein downstream of a stable fusion partner. That, in my opinion, is probably the best way. According to your opinion, the fusion proteins are the best option to increase solubility. Why? Due to the transcription rate, codon level, or better folding amino acid level. So the thing is, fusion proteins, typically it's like when you use a highly soluble fusion protein, it tends to be very soluble, right? So your passenger protein derives the benefit out of it. And that's the best way why, that's the best way to make soluble protein, in my opinion. That's why we think, fusion partners work the best. I'm evaluating the option of outsourcing production of recombinant proteins. Given your expertise in this field, I would like to get a quote from you first. What's the best way to get a quote? Oh, that's fantastic. Thank you for considering us for your recombinant protein needs. We have a variety of protein expression platforms along with a host of protein services to choose from. To get a quotation, you could simply visit our website at www.genscript.com, and from the top navigation menu, you could go to services and then protein services, and each of our pages displays a big red get a quote button now. Get a quote now button, I'm sorry. So you could just click on it, log in, and fill in the required information to get a free quote within one business day. Now everything is online and our system is very simple and friendly to use. Alternately, you could also email protein@genscript.com along with the details of your inquiry, and our technical account manager will get back to you with a free quote. So we hope to be a reliable partner with you as you explore those new frontiers in research. So if you could just give me, I'm still scrolling. What's the maximum size of a peptide protein that can be soluble at all conditions? I wish I knew the answer to that. I'm sorry, I can't. I don't know for sure. The thing is, as I said, one of my takeaways in the summary slide was that there is no magic bullet to address all the insolubility issues in recombinant protein production. I wish there was, but there unfortunately isn't. So each target protein is unique like a fingerprint, and you have to tweak all these conditions to to really come up with a set of conditions that works well in your case. So that's all I can say. But typically, with for E. coli, um, I would see 70, 80 kilodaltons, that's sort of the cutoff, maybe 100 kilodaltons, yeah, that's sort of the cutoff. But beyond that, it gets very difficult. Um, what are the indicators that your target protein is toxic, and how can you remedy that problem? One of the indicators would be that your cells don't grow so well, they begin to die. So that is an indicator that they tend to check out the plasmid. So that is one indicator that your your target protein is toxic. So one way to find out if your target protein is toxic would be to do a stability test, a plasmid stability test, which is it adds some time to your overall experimental setup, but it's worthwhile to do. You could also increase the antibiotic concentration in your media. So for example, if you're using 100 micrograms per mil, just use 150 or 200 of a certain antibiotic, just to put more pressure on the cells. So that's just one way to get around the problem. So obviously toxicity is a big problem. Other things you could do is try the arabinose promoter instead of the IPTG inducible promoters. You want the most tightly regulated expression, so you want to avoid leaky promoters. You could also try a lower copy number plasmid. So that's a few things. Other things you could try out is periplasmic expression. That's one good thing you could try, or you could refold from inclusion bodies. I know it's kind of difficult to push a toxic protein into forming inclusion bodies, but that is one thing that is certainly doable. So your schematic on slide 29 shows a linker between solubilizing tag and the protease tag, but why? I never used it. That's a good question. What I showed on that slide was just a general schematic applicable to any protein, right? You don't need the linker, but it comes really handy, especially if you have difficulty cleaving your target protein. So for example, if I have GST, TEV, and my target protein in that order, I add TEV, right, enzyme, but it doesn't cleave. So adding a linker between GST and TEV can help. In some cases, a linker between your proteolytic cleavage tag and the target protein can also help. So if I just give me a second here. So what are some examples of linker sequences? Okay, so this is in reference to the earlier question. Typically, a linker like GS, or glycine serine, or GGS, or some combination of that nature works just fine as a linker. What about using ethanol as induction? Actually, I'm sorry, but I do not know the answer to that question. I have never used ethanol for induction. I know I've used methanol for induction for when I was working with the yeast expression system. They we use the alcohol oxidase promoter. We have used methanol, but I'm not sure about ethanol. I could check with our production team, and as we post the answers to all these FAQs on our website, I'll make sure I answer that question after I check with them. What is the cost of your potential gold package? How can I get a quote or place an order? Oh, thank you. I'm glad you're considering or looking at our potential gold package. So potential gold is a robust industry first high throughput expression and solubility optimization matrix for E. coli expression. It starts at about $4,800, And to get a quote or place an order, you can simply log in from our website and submit your inquiry online. Okay, just bear with me as I scroll through the questions list. Okay, 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 the method. Okay, I see I'm a graduate student working in a protein biochemistry lab, and I need to make proteins every day. Your seminar will be really helpful to me, and I especially like the part where you talk about factors critical to solubility. Do you have any advice on how I can make my daily work easier? Firstly, thank you. I'm glad that you enjoyed this webinar. So here's the thing, if you are a graduate student or some other researcher who is working in a core facility, or who knows that they'll have to carry out bacterial expression studies every other day, here's my advice to you. Start building a repository of fusion partner based vectors. Now I know it's some work building expression vectors in the beginning, but once you have a good collection, you're going to be very thankful. Actually, you don't even have to create these vectors yourself. You could check to see if a collaborator or a friend already has some. The creation of fusion partner based vectors is time well spent, and these vectors will be an investment in your research. So for example, if you have 10 different ligation independent cloning vectors, you could easily shuttle um, your insert into all of them at once. You could QC them all at once and then transform them into an expression strain and check expression using just one condition. Now it's possible that you will see soluble expression in at least one out of those 10 constructs that you could then further optimize. So basically in doing so, you will eliminate a lot of other expression variables in your experiment. So I think that would be a good investment of your time. I know more questions are coming in. The thing is, so as much as I'd like to answer more questions, because of time constraints, I'm sorry, we have to wrap this session up now. We do appreciate all your questions, and we will do our best to post responses on our website as soon as possible. Again, I thank you all for your time and kind attention, and on behalf of the entire team here at GenScript, we wish you all success in your research. Thank you and have a nice day.